And I would like now to move on to the next session and invite here my colleague to present the Hans Meuer research paper. So, Atem, I knew that. El Taif. The challenge of pronouncing family name. Thank you so much, and I pass to you the baton.
Yeah, thank you so much. Very exciting today to be here to share this Hans Meuer Research Paper Award session. My name is Hatem El Taif. I'm a principal research scientist working at KAUST. So before revealing who won the best research paper at ISC, okay, the click does not work. I'd like to acknowledge the team that worked hard on, all right, there we go. I'd like to acknowledge the team that worked hard with us in making sure all those papers and reviews were received on time, were constructive, and hopefully useful for all authors. In particular, Rich Veduk, my partner in crime, who will be leading the effort for next year. Please, let's give him a shout out. Thank you. And our 6 track chairs that did tremendous work, this year to make sure we have great reviews useful for our papers. We had really to play the trampoline model, as Devesh introduced earlier in his talk with Rich. We have made some abuse a bit here on LLM to try to really reach out to our community and get their papers, their best papers submitted to the conference. We use some sort of videos also to promote and give some visibility for paper submissions. We managed actually to get this open access a few years ago with the help of Michaela and the ISC group that enabled to have all the papers published and available online for free. And also all the authors, presenters of accepted papers at this conference get complimentary registration. We really worked hard in trying to increase the number of submissions. We had to use some inspiration, some imagination, and hey, this is one of it.
We put so much work into our last video. Do you think anybody saw it?
I hope so. I mean, they all should know that in a month from now, they should submit to ISC.
They should, but I don't think they do.
Well, we're going to tell them big time and remind them to do that.
All right, tell you what, let's walk around the floor and see if anyone's even heard of ISC.
Sounds good. Let's do that.
That was a lot of fun to do this. And again, I'm really grateful to have worked this with Rich and, of course, all of our PC committee members and track chairs. So this was really important. We were, at the end, quite successful. We managed to have 125 full papers received and 30% increase. This is 30% increase compared to ISC. We have a total of 132 PC members. About 35 papers made it. That's 27% acceptance rate, a wide range of topics covered in multiple sessions this week at the conference. And we put together a Best Paper Award Committee that decided this year who was the best paper of the conference. So the best paper was given to Saverio, Pasqualoni, with co-authors Marco Canini, Tommaso Bonato, Torsten Hoffler, Lorenzo Piaoli, Daniele Di Sensi. And the title is PICO Performance Insight for Collective Operation. Let's please call upon the authors and the presenters for the award. Without further delay, the floor is yours. There we go. Thank you.
Thank you, Adam. Good morning, everyone. My name is Saverio Pasqualoni, and I'm very delighted and honored to be here. Today, I will present to you our work, PICO, Performance Insight for Collective Operation. First of all, I want to thank all my advisors and collaborators from Sapienza University of Rome, King Abdullah University of Science and Technology, and ETH Zurich. This work presents a new framework to benchmark collective operations. First of all, why collectives? Collectives are everywhere. Collectives are core primitives for distributed application. When we talk about collective, we think of communication pattern, such as an all reduce or a broadcast, that happens among a group of nodes in a distributed system. And then we use this collective to move data around in predefined manner. Collectives is very well known that can dominate the total runtime cost of application. Study shows that upwards of 66% of total MPI runtime on production supercomputer is spent on collectives, while recent mixture of expert training shows up to 32% of total training time spent on collectives. So it's something that is present both in classic HPC that in modern AI training. Moreover, we have collective operation in many different flavors. We have a lot of different libraries that implement those collective communications. And thus, we have many choices, and we may use collective without even realizing it. So those are just some of the main libraries, and in the case of MPI standards, that implement collective operations. But unfortunately, tuning those collective operations remains a big challenge for a lot of reasons that I will now show to you. First of all, modern networks are highly heterogeneous. This is the schematic of LUMI, a European supercomputer, and we can see how we have inside a single node a lot of different networks with different connectivity at different speed. Then, when we move outside of the node, we go from intranode to internode connection. We have to have an allocation of the topology of the machine. This is what is called a dragonfly topology, in which we have a group of nodes that are fully connected with full bisection bandwidth, and those groups are more sparsely connected among them. What we do is that when we ask an allocation with Slurm or whatever we are using, we get some of those nodes from the cluster itself. We can have some nodes in the same group, so we just will rely on those local links. Or if we ask for a very big allocation, which is often the case for big job, we have nodes among various groups, and this will have the unwanted consequence to rely on those global links that can be a source of contention. This can be very problematic for collective communication, and I will show you why with an example. Here, I will show how two very similar broadcast operations, binomial broadcasts, can have a dramatically different effect that is not so clear with just a cost modeling perspective. This is a distance halving binomial broadcast, in which here I have data on node 0, and I want all those 8 nodes to have the data. What I do is I send the data to the node at distance 4. So then, in the next step, I have this communication between node 0 and node 2, and node 4 and node 6. And in the last step, I do the remaining communication. On the contrary, I can do what is called a distance doubling binomial broadcast. In a distance doubling binomial broadcast, instead of halving the communication distance, I double it every round. Through a cost model perspective, I can see here that I have the same number of steps and same communication volume. But take in mind that this happens on an allocation of a cluster. If I have an allocation like this, well, I don't see a lot of difference between those two algorithms. Instead, in this case, something strange happens. Now I will map this toy example to this graph, and we can see how, with the distance halving binomial broadcast, we have 3 messages on global link, while with the distance doubling binomial broadcast, we have 6 messages on global link. Again, more results will be shown later. This is just to give you an idea on how topology and allocation plays a role in collective communications. Moreover, collectives cross many different software layers. This is a simple schematic from how we go from an application that can be an HPC simulation or AI training or whatever, and those applications will rely on communication libraries such as Nickel, Recall, MPI, or HMEM libraries. Again, those libraries themselves will rely on lower-level libraries such as UCC or UCX, and those will rely on network-level libraries such as libverbs or libfabrics that then, in turn, will communicate with the hardware. So we have many different layers going from the application to the hardware, and each one of those layers will have its own tuning parameter that will change the performance of those collectives. Here, for example, in Nickel, we can see how in Nickel 2.19, we have 67 documented variables that can change collective performance, and more than 100 in modern Nickel versions. In OpenMPI, we have dozens to hundreds of MCA parameters, and those are build dependent. Again, similar thing with UCX and with UCC. So each one of those single libraries, and I can be using, for example, MPI over UCX, will have its own stack of parameters that I may need to change in order to get the best performances available. And this is not always so easy to see. Moreover, we want to understand what happens in a collective. When we think of a collective operation, we think of it as a black box that has a start time and an end time. And we intend to measure this time. But what actually happens is that the collective is an algorithm. For example, this is a Raben-Seifner all-reduce. And here we have, this collective that has, we can say, three phases. A data movement phases in which data is moved to and from temporary buffer. And then we have a reduce scatter and an all-gather phase. Then this collective itself can be divided into multiple communication rounds. And those communication rounds can then be divided into steps. For example, in the case of the reduce scatter, we can have both a reduce step and a communication step. What is usually being reported by the state of the art is just this total runtime, but we may be interested in understanding what's really going on underneath. So that's the main question. How do we move from end-to-end benchmarking to a diagnosis of collective operation? Moreover, we don't want to just know which collective is slow, but where time is spent, and moreover, why this happens and under which system condition. So those are the main question and motivation that led us to the design of PICO. PICO is a novel benchmarking framework, collective benchmarking framework that was built with those four ideas in mind. First, fine-grained attribution. We want to reveal which algorithmic step represent a real bottleneck in our execution. Moreover, we want a portable experiment control to compare those results across different libraries, MPI, Nickel, and across different systems. We want controlled algorithmic baselines to isolate algorithmic differences from backend differences. And we want to ensure experiment reproducibility. So an experiment from itself is not useful if we don't know what is the full context in which this experiment is run. So we want to capture as many metadata as possible, software version, transport version, environment variables, and allocation information. This is very important for us. Now, we will go, I will introduce to you very fast the architecture of PICO. And here you can see at the top that we have some descriptors. And those descriptors then go through a benchmark orchestrator that in turn called a benchmarking harness called PICO core that then registers the results. Now we will go into a little bit more details into those part. PICO is built around the idea of decoupling what to run from how to run it. So we have a test JSON that describes collective algorithm selection, experiment dimension, result granularity, pressure, whatever information I may want to give to this test. And then we also have some environment information that are captured by some descriptor. Those descriptors describe software and modules, hardware information, provide Slurm templates, and when I want to use PICO on a new machine, I might need to just rewrite those new environment JSON because the test JSON are something that is cross-compatible across different systems. Moreover, we decided to also build a easy TUI in order to let the user understand what are the possibilities that are available in the test. So this TUI is going to be used to create those test descriptors. Then we move to the benchmark orchestrator. The benchmark orchestrator resolves those descriptors and applies the platform setup. Moreover, it submits and manages Slurm jobs. Then the PICO core is the real benchmarking harness. We can see that in a similar vein of what also is. It initializes backend context and executes and records timing. Alongside PICO core, we have also an optional libraries that contains reference MPI implementation taken from the two major open source MPI libraries, MPitch and OpenMPI. And moreover, it contains optional instrumentation for those collective. I will show to you what this means. This is the pseudocode of an all-reuse. And here, with this pseudocode, you can see that we can tag semantically meaningful part of the collective. And those tags will then, at runtime, be transformed into a MPI W time. And I can do this at the granularity that I choose. And this will allow me then, in post-processing, to really understand what's going on with this collective. Then we move to the result collection. Alongside the results, we also capture some software hardware information, environmental variables, or our location. So we have a clear distinction between the data that is gathered and the metadata that is gathered. And this can be fed then to some post-processing tool that will allow us to, that will help us. For example, we have a network traces that will infer what is the possible network congestion given an allocation and algorithm that is being run. Or a tuning file generator that, given some test, can then generate an optimized version of a two-tune library. And then we also have some visualization scripts that are very useful to do fast diagnosis. Now we will move to the evaluation part itself. First of all, I want to highlight this heat map. This is a test of an old reduce done on Lumi. And here we report the difference of runtime between the best available or reduce algorithm and the one chosen by default. Here we can see that we have a very large part of the data, especially on big vectors, in which a median of 40% is, we have a slower default than what is already available. Moreover, in the worst case, we have only 20% of the available performance, and those are performance that are available just by changing and tuning algorithms. And in this, we have a tool that can help us, once we do the test, to really tune those libraries. More results are also available in the paper from Leonardo and Mare Nostrum 5. Then I want you to remind of, on this example of a binomial broadcast, because now we will show some results of it. The importance of locality is shown in this graph. This is an MPI broadcast done on Leonardo on 128 nodes on 4 processes per node. And here I can show how the binomial halving is 2.5 faster than the binomial doubling. And using the network tracer tool that I showed before, this can be easily explained, because here we can see that with the allocation from which this test was done, we can see that the binomial doubling has a 96% of traffic on global link, while the binomial halving only 29%. So this is very important. It is not at all something that people think about. Then we can move to fine-grained profiling. Again, we have the example of the beginning of the reduce shown at the beginning. Let's say that now we want to understand what do I do in how much time is spent in communication, in reduction, and data movement. So I tag the collective, and I get this test result. Here I can say that I can easily see that I have a very, from up to 16 kilobyte, I can see a very latency-dominated scenario in which communication is almost 95% of the total collective runtime. Then what happens here, probably we can see that we have a movement from communication to intranode bottleneck, and those intranode bottlenecks are reduction and staging of data to and from temporary buffer. Then when we move again, we move to another phase in which communication starts becoming, again, really important and really predominant, but those intranode bottlenecks that we saw before still appear and are still something to be taken care of. So what we can say is that end-to-end timing reveals only a change in performance, while fine-grained profiling reveals where this change originates. Explaining it requires still understanding how the hardware and software stack are stressed within each single algorithmic phase. So I need to understand both what I'm running and where I'm running it. Then at the end, we had a question. We did a lot of micro benchmarking, and we wanted to ask, but how this can change the total runtime of application? And to do that, we use some AI traces. In particular, we asked the question, what if for the same application trace, we use a different collective strategies? So we have those nickel traces, and with the Atlas simulator, what we did, we have the traces that log collective order, message sizes, and communicators. And then we change, via the Atlas simulator, algorithms and protocol. And so the question becomes, using the same workload, we want to measure the impact on iteration time of those changes. And here are the results. Here we have tested on Llama 7 billion and Mistral mixture of expert. we can see, first, a little analysis on the collective views. We can say that on Llama 7 billions, we have upwards of 90% of all gather and reduce scatter of up to 14 megabytes. And here we can see that by simply changing algorithm to the path algorithm that was not chosen by default by the nickel runtime, we can achieve 21% faster iteration runtime on 16 GPUs and 44% faster runtime on 120 GPUs, just by changing algorithm. Again, Mistral Mixture of Expert instead sees fewer collective of upward to 1 gigabyte. But here we see that the default is nearly optimal, and we don't see measurable gain in changing algorithm and protocol. And this shows how, and this is still something important, because it shows how tuning collective can yield something that is very great of upward to 44%, or maybe the default choice is already optimal, but we don't know that up until we do this tuning. And now we move to conclusion. First of all, we showed the importance of collectives and why they are so hard to tune nowadays. Then we explained PICO, its philosophy and its design. We moved to the insight generated by PICO, really understanding what's going on inside those collectives. And then from those insights, we moved one step further and analyzed the effect of those insights that have to a total runtime of an application. So thank you all for listening. My name is, again, Saverio Pasqualoni, and if you have questions, I'm open to answer.
All right, so we have time for a few questions from the audience. There is a mic in the middle on the L if you want to ask a question. All right, I have one question. So you talked about PICO for collective operation. So what about non-blocking or asynchronous collectives?
Okay.
Does PICO or PICO handle that? And what would it take to extend PICO feature for that?
At the moment, still does not account for non-blocking collective operation, but this is a future step in research. It's something that we were discussing about, but it was something that was missing due to just development time. But it's not,
Sure.
it's not really something that PICO cannot do. It's also true that micro-benchmarking is slightly different when it comes to non-blocking collective communication, so there are some things that needs to be readdressed, but I don't see it as a very big problem.
Got it. Thank you.
I have a question, indeed. Yeah. Fantastic talk. I have a question about reproducibility and aspect of non-determinism in execution. When we have collective communication, that is one challenge, especially at large scale. Can you elaborate how PICO could be used to understand aspect of reproducibility and non-determinism, if it can, or if it is perhaps future work?
So what PICO does is that it saves as much as possible as the current state of the system. So all the environmental variable use, all the build information of the software version, and also in the platform descriptor, you also have the information about the hardware itself and how SLARM is set up. So getting all of this information, we can have a clearer view on why the reproducibility aspect of this tool. Then again, it's not a silver bullet. It does what it can to ensure that all this data is collected and stored in a safe manner. But again, reproducibility is always a big task.
Thank you.
You're welcome.
Thank you. Any other question from the audience? All right. Okay, let's thank again the speaker. Congratulations. All right, that concludes the award session today. Enjoy the conference and see you around. Thank you.